So, well, anyway, hello, welcome back. We're going to have a keynote speaker from Accenture who will be talking about Accenture Tech Innovation.
Yes, and our keynote speaker is Hassan Nasseri. He's actually a technology innovation manager, and he is working in fields of artificial intelligence and quantum computing. He's an author of numerous publications and also some great awards from Nokia and from Huawei. He has also worked in Huawei.
Well,
what's the speech title, Luis?
I've already said it. It's Accenture Tech Innovation. So,
welcome, Hassan.
Passing over to Hassan.
Thank you. Okay. Hello, everybody. And I present today quantum computing technology at Accenture. Accenture is doing a long range of innovations, new technology. We are doing extended reality, quantum, blockchain, and many other new topics. Quantum computing is one of the areas that I have been very active in recent years at Accenture. And I go quickly first over what is quantum computing and what's the promise of quantum computing, and then show some of the use cases that Accenture has built in this area. So that is all about complexity. There are certain problems in the world that are too complicated, and there are many of those problems. For example, if you take a postman who wants to deliver just a small number of packages, like 100 packages in a town, there is no absolute solution. We don't know what is the optimal solution for that. We cannot solve such a problem. And I have just some numbers here. For example, if you have 100 packets, the complexity is 2 to the power of 100 to combinatorially search and find the optimal solution. The number of atoms in the universe is much smaller. And even the age of universe wouldn't suffice to solve such a problem. Of course, there are heuristics, and we can find suboptimal solutions. This is just an example to show that there are many complicated problems. And even like everyday problems can become very, very complex. There is also other class of problems which are not necessarily very complex in a way that we can solve them, but it takes too long to solve them, so they are not practical. We need short time to solve them, like in market finance and things like that. Currently, we have silicon technology. We are building transistor-based computers, and they are not growing as well as last years or last decades. So there will be more difficulties in future to increase the computational power of existing technology that we have. So the idea is that we need to find some replacement technology, some new technology that will replace our current our current computing technology. And one of the candidates for this is quantum computing. Quantum computing has the promise that it will be able to solve certain problems much faster than classical computers. On that premise, it can change many sectors of the industry. So some problems that are intractable to solve nowadays, we will be able to solve. And some problems that nowadays take too long to be practical, we will be able to solve them in shorter time. Again, this is a promise, and we are building on that promise. So how does it look like? A quantum computer does not look like a normal computer nowadays. The technology is completely different. It's not a faster supercomputer. It's fundamentally different from our current computing technology. Information is in a quantum system, and it is governed by quantum mechanics and runs specific algorithms. So we need specific algorithms to be able to run them. So here it's IBM's lab. You see some of these quantum computers, a couple of them there. They are big cylinders hanging from there. So they don't look like, they look like maybe a replica of some, like half a century ago, how computers look like. So they are huge things. And this is also other pictures showing inside of that chandelier. If I can find the laser thing here. OK, good. So this is inside of this canister. And then this is a fridge, more or less, cooling down to millikelvins, and even like very low temperature, so almost close to absolute zero. And then there is a chip inside that cooler that works. This is other type of a quantum computer. This is ion trap working with lasers and trapping ions and creating qubits in a quite a different manner. Anyhow, as you see, at the moment, these are more or less lab setups, not ready to be shipped or put into your pocket or things like that. So it will take some time. There are two main phenomena that help us to get efficiency or so-called advantage with quantum computing. One is quantum parallelism, and it means that we can parallelize some information or some processing. And one of the main reasons for this parallelism is that the space inside the quantum computer grows exponentially. So if you have n qubits, you have 2 to the power of n components or vectors in the vector space that defines that quantum computing system. Of course, not of all whole space, this whole space is not available to us. It is inside the quantum computer, but there are mechanisms that we can exploit this huge space and use it. Other area is quantum interference, other phenomenon, and it is more like about entanglement, which also helps us to get quantum advantage. But in order to build a quantum computing algorithms and software, you don't need to worry about the physics. Because physics is a matter of interpretation, it's complicated. You just need to know about the mathematics, which can be actually sometimes simple. And at least it doesn't require interpretation, so you don't need to think about multiple universes or things like that. You just have some numbers, and you multiply, and you get the result, and it doesn't get too complicated. I cannot explain today how quantum computer works or brings advantage to us in this quick session, but this is one analogy. It doesn't explain everything, but it's one analogy that if you want to search a maze, you need to start with multiple places and go through the maze and finally find the solution. One idea in quantum computing is that we can evaluate all of these at once. So kind of a parallelism, but you don't need to run parallel instances of the problem to get that parallelism. You run one instance of a problem, and single instance of a problem is able to evaluate all possible inputs, because all the possible inputs can come as a superposition. So we can create one state which encodes all the inputs at once. We evaluate that, and then we can get a solution which is the optimal solution or feasible solution with basically some parallel mechanism. So this is algorithms like amplitude amplification use this idea. There are two main types of quantum computing technology. One is the annealing, and other one is quantum gate model. Quantum annealing is not a universal quantum computing. It can solve certain types of problems, mostly optimization problems. And then we have a quantum gate model, which is a universal quantum computing. And it is, at the moment, it is much smaller than annealing methods. For example, IBM, Google, and others mostly are building that system. It is much smaller than the annealer, but it's a universal system that can solve much larger varieties of algorithms. So we have a full stack in quantum computing. So not everything is related to the hardware. We have quantum hardware, and then on top of that, we have quantum machine code. We have gate model, and then we have algorithms, and then we go upper stack, and then we get software and use cases. And in all these stages, there is already active work and development and people building algorithms and solutions. So I wanted to show some demos, but we are not able to run through them. But I can, at the end, I will go through a list of demos. Let's now look at what kind of problems a quantum computer is solving. There are three main categories that we are currently addressing. One is the machine learning algorithms, the other is the optimization, and then we have sampling and simulation. Let's go through them one by one. In optimization, we want to find a solution which is the best solution to a problem which is modeled. So we have a model of a system. Let's say that we want to move some stuff from point A to point B through multiple routes. We model the whole problem, and we want to find the shortest or minimum cost solution. And this is bread and butter of the industry. In all the industry, you have optimization problems. And we have a large number of algorithms currently available in quantum computing to do optimization. We have both for quantum annealing system and also gate level quantum quantum computers can do optimization. Then the next area is AI and machine learning. We have a list of algorithms that are built for AI and machine learning. Optimization algorithms already are building blocks of most machine learning algorithms, but other than that, there are clustering methods like quantum support vector machines, there is quantum neural networks, and then other algorithms built for machine learning. The other main area is simulation. I mean, this is a famous note from Richard Feynman that if you want to simulate a nature, you better do it with quantum systems, not with classical methods. And that gives us some idea of why actually quantum computing is good for simulation, because many of the systems that we are simulating, say quantum chemistry, deals with quantum mechanical phenomenon, that when you map it to a quantum computing system, there is more or less a direct map. So there is no much overhead in building such a mapping. Also with quantum physics. But there is also other kind of simulation. For example, you can simulate classical systems like thermodynamics, and those can also work. In general, the idea of quantum advantage is that by solving a problem on a quantum computer, you will get some sort of a time or space advantage in terms of complexity. And that can be either exponential speed up, which is proven in theory and also in practice that you can get exponential speed up for very certain problems. Or it could be quadratic speed up, which you get at least like 1 order of magnitude faster. And that is for more generic setup problems. You can get that kind of a quadratic speed up. We have 3 different categories in general of the algorithms. We have exact algorithms, which are finding the exact solution to the problem. We have approximate algorithms like VQE or QNOA. These algorithms are sampling algorithms or algorithms that are built for near-term quantum machines, and they find approximate solution. And then also there are hybrid algorithms, which are hybrid between quantum and classical systems. I very quickly go over the roadmap of quantum computing. This line of research started a long time ago, from Richard Feynman's time. But it has been progressing very quickly in recent years when we have access to machines. And you can see here, for example, roadmap from IBM, roadmap from Google. Companies are releasing roadmaps. Some of those roadmaps are actually met. Some of them change over time. But the overall idea is that there will be quantum computers, let's say in a decade, but actually we are hoping that in much less time, in few years, there will be quantum computers that will solve some problems better than classical computers. At the moment, we don't have any. So at the moment, we don't have any case that a quantum computer can really be bring advantage to a business. Of course, in research, in chemistry, there is advantage because you already want to explore those areas. But to real business of the industry, we are not using quantum computing for their business cases. But in few years, there will be. And then, as you see, for example, here in IBM's roadmap, actually, in a decade, they are building like 1 million qubit computers that will be able to solve some real-world problems. So the field is growing very fast, and there are projections that in, say, by 2030, we will have some viable optimization algorithms running, and forward, we will have more and more use cases. There is a whole stack of companies and methods for quantum computing, from bottom, building hardware, to building API layers, cloud migrations, cloud solutions, to migrate, for example, from classical systems to a quantum system, and there are backend services, and there are use cases and applications. So there's a whole stack. And it's a very active area. Many startups are already starting to build, and even in Finland, we have several startups in this area. So this is a quite active research and development. And at Accenture, we have a team working on it. We have this practice for several years, and then we have been building many demos, prototypes, and research, and patents, and so on. So what I do now is that, okay, this shows a global network that Accenture has actively working on quantum computing. What I do now is that I quickly go through some of the industry cases that we did. These are not applications that we are currently necessarily running for somebody. These are prototypes, proof of concept, proof of value. Sometimes they bring also real value actually to a case, but these are mostly demonstrations that we did. And the idea here is that we are mapping a business problem to a quantum system. We are showing that we are able to do so, and we are showing that it brings some meaningful result, even though with a limited size of a quantum computers that today they are not business relevant. So the first one was molecular simulation. Here we did it with Biogen, and the idea was to compare molecular structures and show that if their structures are similar or not. And we showed that this problem can be solved, of course, again, for small molecules. The next one was, again, molecular comparison, very similar thing. Then we had protein folding. In this case, we were trying to find the 3D structure of a protein, and we used reinforcement learning actually to build a quantum algorithm which can solve the problem. This was a research by Rigetti. Rigetti already published a paper on that. If someone is interested, can check that. We showed that some meaningful results can be obtained. Again, for very small structure, you see here in this example that is shown, there are like only 8 basically atoms in the protein, and it can scale up to 10 or something. And after that, we need a bigger quantum computer to be able to solve it. Kidney exchange. This is kind of a graph matching problem. So the idea was that there are some donors and some patients who need kidneys. And then this is actually the database was from US. And this is some graph problem that you are trying to match. And again, we were able to map it and solve it with D-Wave annealers. Q-Power is an intelligent power scheduling for power networks, for smart grids. Then we have QRAD, which was comparing the images for radiography images, robot arm demo. Then here we are basically finding the shortest path for a robot arm to move. In an industry, say in a drilling, you want the robot to drill holes, or you want the robot to do some welding in a factory. There are like hundreds of points that robot needs to travel, and just finding the most efficient path is a complex problem. And this is an example of a traveling salesman problem that you see in a case that is like a robot arm, a very different case, but similar problem is applicable. Recommendation systems, and sorry that I'm looking back because I don't remember the order, but streaming, classifier, ticket solution. But I go fast over these, maybe something interesting comes up. Yeah, frequency optimization was optimizing the frequencies for power grids. And that's it, thank you. I just went quickly over all of these demos, but if someone is interested, you can reach me out and we can discuss more details. Thank you.
Okay, thank you very much, Hassan. Thank you.
Thank you so much.
Thank you very much.
Thank you so much, Hassan, and see you at 5:30.
Yes, so we'll be back at 5:30 with the matches beginning.